So what happens when you apply the Euler-Lagrange to a function and it returns a value of 0? So let's look at an example here. We had the integral from a to b of y squared plus 2xy y derivative by dx. So when we apply the Euler-Lagrange to this function here, we're going to get partial f by partial y. So the first term will give us the 2y. The second term, the 2xy derivative, will act like a constant. So we differentiate y with respect to y, it gives us 1. So that just gives us 2xy derivative. So that's the first little bit. So that's going to be minus d by dx of partial f by partial y derivative. So again, 2xy acts as a constant, and it's just partial y derivative by partial y derivative, which just gives a value of 1. So you just get this 2xy. If we differentiate this again with respect to x, then we use the product rule for differentiation. We need to use the product rule because we're differentiating with respect to x, and we've got a function of x here. We've also got y, which is also a function of x. So we need to, there are two functions multiplied together. So we're going to differentiate the one and multiply with the other, and then differentiate the other and multiply it with the first one. Okay, so that's going to give us, when we differentiate the with respect the 2x here with respect to x, just gives a value of 2 times the y, and then we can differentiate the y with respect to x, gives the y derivative times the 2x. So we're going to be left with this term here minus this term here, which gives a value of 0. So we can't go anywhere there with the Euler-Lagrange. But a thing to note here is that in this example here, you can see it's quite straightforward that d by dx of xy squared is the same as this y squared plus 2xy y derivative. Okay, so you can see that there. When we multiply this out, we get this here. So it means then that whenever we're taking the integral of this function here, then we're just going to get back to our original function, which is our xy squared. So it's going to be xy squared from a value a to b. So whenever we put the values for a and b in for our x, then we're just going to have our b y squared yb squared minus a ya squared. So that tells us here that the value then for if the Euler-Lagrange equates to exactly 0, then the functional is a function of the endpoints only. So you can see these here are simply the endpoints y of b and the endpoints y of a. So it's going to be b and y of b and a y of a. So we've purely got a function of purely of the endpoints. So that's a little, it's not a proof, it's just one particular example. I have a proof in the course slides and also in the course notes. So if you want, you could have a read over that, and if you've got questions and you don't understand, you can always get in contact with me. It's a bit involved, but if you're interested, you can always work through it. That's all there is for this video. I'll get you on the next video. Goodbye.